By now it should be clear, I think, that global warming is a problem, and there are many things we can and we should do. One of the things obviously is to produce cleaner electricity. And if we look at European countries, producing cleaner electricity will probably mean producing more electricity by wind energy. Wind energy will probably make up roughly half of the energy mix if we make the transition towards clean energy. If we talk about wind energy, then many people think about the really large wind turbines. These are wind turbines that can power almost 10,000 households. If we look at the smaller turbines, then we're talking about machines that are much, much less powerful. So the big ones are in the megawatt range, and the small ones are in the kilowatt range. So the powers are roughly 1,000 times less. Of course, it also means that they're much smaller and that their impact is also smaller. And the most obvious place to put these small wind turbines is in farms or in small enterprises. Surprisingly, small wind turbines can also play a role in producing electricity locally in an urban environment. Because in some places in cities, wind conditions are actually excellent. If you go and stand on the top of the roof of a high-rise, then you'll find wind conditions there that are comparable to those that you find at the seaside. So very, very good wind conditions. That also means that if you would place a wind turbine on top of the roof of one of these high-rises, you'd have very good energy productions. So wind turbines, small wind turbines, may play a role in producing electricity locally in cities. A question that is often asked about small wind turbines is whether these wind turbines are economically viable. The short answer is sometimes. A somewhat more elaborate answer would be to look at three main aspects. One is the market of small wind turbines, the other is the wind resource, and the third point then would be the careful placement of these wind turbines. The market of small wind turbines is a very immature market. What that means is that many wind turbines on the market are not good at all. And this is a very different situation than in a mature market, as you would find, for instance, when you would buy a car. If you would go to the Salon de l'Automobile and you would buy a random car, then the chances are very large that you'd find a more than decent car. This is completely different for small wind turbines. If you would go to a proverbial salon of the small wind turbine and you would buy a random wind turbine, the chances would be very large that you would come back with a bad product. This does not mean that all small wind turbines are bad. There are actually very, very good products on the market. But because the good products are only a very small fraction of the total market, you actually need expert knowledge to pick the right turbine for your purpose. A very important point is that you need wind if you want to install a wind turbine. Even the best wind turbine will not produce anything if there is no wind. So you really need to assess very, very carefully whether there is enough wind on your site. So this is really a very important point for economic viability.
In a follow-up project, we will look at ways to replace the blades by what are called smart blades in order to control the flow around the blades. We hope to, on the one hand, reduce the aerodynamic loads and on the other hand, increase the aerodynamic performance.
If you want to know the wind speeds on your site globally, then you need to measure. That's what we always do. We go on the site and we put the instrumentation there so that we know the wind speeds.
We have performed measurements of the loads, thus vibrations and strains on the turbines. We have performed electrical and mechanical power measurements of these turbines. We have performed wind measurement studies on a number of rooftops. We have even measured the noise on such turbines.
On a typical wind measurement station, you can find a data logger and the wind measurement equipment. The data logger measures every second the data from the wind measurement equipment and store it on a SD card or USB key. The typical wind measurement equipment are a anemometer to measure the wind speed horizontally. Because of the complex terrain, we are not sure that the wind speed is always horizontal, so we installed an ultrasonic anemometer to measure the wind speed in 3D. And finally, we also installed a wind vane to measure the wind direction. We also measure the temperature, the air pressure, and the humidity.
To determine the best possible position of your wind turbine on the site, you would actually need to know the wind speed in every single point of your site. Of course, you can't measure on every single point of your site. That would be much too expensive. So to solve that problem, we make computer models. If you want to determine the best possible location of a wind turbine on a site, then a good thing to do is to use numerical simulations, because it's just way too expensive to measure everywhere. And these are the kind of simulations we do. You should consider this as a kind of a virtual wind tunnel. And what you can see here, for instance, is the way the wind blows over a high building. These are what we call streamlines. The wind is coming from the right side, and you actually see the way that the wind blows over the building. And this is what these kind of computer simulations tell you. And if you then, for instance, look at the top of a building, then here the red colors are high wind speeds and the blue colors are low wind speeds. So obviously you should put your wind turbine there where the wind speed is high. So we can actually determine from our computer simulations that these regions here are good locations for a wind turbine and not the blue ones.
Our research group evaluates all the possible impacts that a small building-mounted wind turbine might have on its environment. These impacts are manifold: biodiversity, vibrations through the building, air traffic, and so forth. An important impact is the shadow flicker effect. On a sunny day, the rotating blades cause a flickering shadow that might be disturbing. This is why it exists clear regulations in Flanders and Wallonia, limiting this effect at 30 minutes a day and 30 hours per year. For each studied site, we developed 3D models to study the shadow of a wind turbine on its environment. The limit was never reached because the rotor is very small and the shadow runs very fast. Another impact is the noise. On a high-rise rooftop, it's often not an issue for these turbines. Actually, we visited some rooftops where the noise from the ventilation system or the wind was already such loud that we had troubles to hear each other. In all cases, a noise study must be performed to be sure that the impact will be negligible.
We have performed analysis of the structural impact of rooftop-mounted wind turbines on the buildings on high-rises. For this, we have collaborated with Bureau Grèche from Liège. They have performed simulations to study the impact of small rooftop-mounted wind turbines on different high-rises here in Brussels. The result is a knowledge of what the resulting vibration levels will be for the different floors of the high-rises. We have shown that the vibration levels of rooftop-mounted wind turbines for our studied cases will be very low or even unnoticeable.
Of course, every site is different. If the installation of a small building-mounted wind turbine is foreseen for a rooftop, the owner should perform a full feasibility study before installing a wind turbine. As required by the Belgian legislation, we develop plans, sections, mock-ups to help the understanding of the projects for the urban decision makers.
Our faculty has 3 wind tunnels at the disposition of the students for their aerodynamic experiments. We have the small visualization wind tunnel with a test section of 20 by 37 centimeters. Then a self-made open loop wind tunnel with a test section of 50 by 70 centimeters. And last but not least, the biggest wind tunnel of our faculty, 2 meters wide for 1 meter tall. Here you can measure large scale models. Students can easily measure the aerodynamic characteristics of blades, turbine and scale models. Here we can see that we can complete projects from design to manufacture to experiments. Every project starts with a first design, a first concept, in this case a vertical axis wind turbine. So we first need to draw the turbine in a 3D software. Here you can completely define the turbine. After the drawing, we also require some strength analysis, like finite elemental analysis, for safety and security purposes. Both models were made in FabLab with all the tools that is here available.
If the owner of a building still desires to install a small building-mounted wind turbine, the last step is the building permit preparation. Our research group wants to help and guide the owner through all procedures before the actual installation of the system.
One of the core strengths of our group is that we combine a sound theoretical basis with practical skills and craftsmanship. For instance, in the Wintegrate project, we have performed CFD simulations of complex flow over high-rises to ensure a proper microsighting of turbines. But at the same time, we have performed measurements of turbines in the field. I think that this palette of expertise has put us in the vanguard of wind energy studies.